Question 6 is about energy levels in atoms. Now, I'm not actually going to do the question that's in the book. I'm going to do another very similar question that uses the same ideas instead. If I just put the two questions sort of side by side for a moment, one of the things we notice is that the question in the book calls the lowest energy level, which we have to assume is the ground state, it calls that n equals 1, and the next one n equals 2, n equals 3, and so on. The example I'm going to do doesn't use n, it uses little subscripts to the energy levels, and it actually labels the energy level, and the one that's labelled level 1 isn't the ground state of this question, it's the next state up. So it's as if in this question it's using the numbering system where the ground state would be level 0. So we've seen two questions that seem to use different systems, so we have to sort of be clear in our mind that there isn't any one system that is necessarily the way the examiners are going to work. So we just have to be sort of aware to sort of check what the numbering is. Just make sure that we use the system that agrees with whatever diagram we're given in the question that we're dealing with. So whether we call the ground state level 1 or level 0 doesn't really matter as long as we do what the examiners expect us to do on that occasion. So in this question it says the diagram represents some of the energy levels of an isolated atom. Now when it says some of the energy levels, what that means is it's missed some of them out. And in this gap between level 2 and the ionisation level, there would actually be lots and lots of other energy levels in there that we don't need to worry about. And in this example, like the example you've got in the book, it says you've got an atom that's isolated, in other words it's not affected by any other atoms, and you've got an electron that's coming in from outside. So this atom is probably part of a gas that's in a tube that's been made to conduct electricity. Don't need to worry about the details, but that's the way in which you'd probably end up having electrons whizzing and hitting the atoms. And it tells you how much energy this electron's got, the one that comes in from outside. It says it makes an inelastic collision. Now you haven't really learnt about inelastic collisions for Unit 1. All that means is a collision where energy isn't conserved, so the electron doesn't bounce off with the same energy. The electron that comes whizzing in is going to lose some of its kinetic energy. And it's that energy that the electron loses that this whole question is about. Because if the electron that comes whizzing in loses energy, it must be that the atom has gained the energy. And that's what we're expecting this question to be about. So the electron comes in, that's how much energy it's got, it makes an inelastic collision with the atom in the ground state. So to begin with, this atom has got its electron in the ground state. Notice also, by the way, that the question is talking about the ground state being the ground state of the atom. Sometimes we talk about the ground state as being the ground state of a particular electron in the atom. But it all comes down to the same thing. The first question we've got to answer, we've got this electron coming in. Show that the electron can excite the atom to level 2. So that's the atoms are initially in this ground state, so there'll be an electron in the ground state, and it says got to show that there's enough energy for the electron that was in the ground state there to be promoted up to level 2. So what we need to know is how much energy does it take to get from the ground state to level 2. And the way we do it, we just have to look at the difference in these numbers. It's going from minus 2.18 times 10 to the minus 18 up to minus 2.42 times 10 to the minus 19. So the amount of energy the electron needs to gain to go from here up to here, we find just by taking the difference between those two numbers. And the difference in energy levels, 1.94 times 10 to the minus 18 joules. And if we accidentally got our signs mixed up, because it can be confusing, everything's got minus signs, we do know that for an electron to go from the ground state to a higher level, you've got to put positive energy in there. So if you accidentally get both signs mixed up and you with a minus sign in the answer, just sort of use common sense and realise that it's got to be positive energy to make the electron go from a low level to a higher level. So I'm going to write there, delta E, the change in energy, is 1.94 times 10 to the minus 18 joules. Now that, of course, that hasn't answered the question. All I've done is I've worked out how much energy it takes to get the atom to go from the ground state to level 2. Where's that energy going to come from? Well, what's bringing energy in is this electron that's coming from, that's not part of the atom, that's part of an electric current somewhere, comes whizzing in, bumps into the atom, and it's going to give some or all of its energy to the atom. So the question is, does it have enough energy to be able to provide this much energy to the atom? And we'll look at how much energy the electron had. It had 2.0 times 10 to the minus 18 joules. So does the electron coming in have enough energy to provide the electron that's in the atom with the energy it needs to get to the next level? Yes, it does, because that number is bigger than that number. So if we just explain that thing that we've calculated there, that's the energy required for the transition to occur. Incoming energy of the electron is 2.0 times 10 to the minus 18 joules. So electron does have enough energy to cause transition. Right, next part of the question is now talking about this electron that's coming from outside. It's bumped into the atom, it's given up energy to the atom. After the collision, how much energy will this electron have left? Well, it started out, came in, it had 2.0 times 10 to the minus 18 joules. It gave some energy to the atom, and the important thing about energy levels in atoms is that the atom can only accept just enough energy to make a transition. So to make the transition it took 1.94 times 10 to the minus 18 joules, and that's the only amount of energy that the atom can accept. It can't accept any more than that, so therefore the electron must be left with some energy left over. So we take what it started with, we subtract what it was able to give to the atom, 0.06 times 10 to the minus 18 joules. Right, the next part, calculate the shortest wave of the radiation that can be emitted by an atom in level 2 returns to the ground state. So the atom in this energy state is going to go back to the ground state, and it says find the shortest wavelength of radiation that can be emitted. That suggests that there's more than one possibility. And we've got to remember that if an electron's in level 2, it's possible for it to drop all the way back to the ground state in one move, or to drop down first one level and then the rest of the drop. So you could do it either in one stage or in two stages. So you've got three different energy photons that could come out. Now the question is the shortest wavelength of radiation. So if you want radiation with a short wavelength, that's the same as saying radiation with a high frequency. And if the radiation's got a high frequency, that must mean that the photons have got a lot of energy. So we need to find what's the photon with the biggest energy that can come out. And the photon with the biggest energy must be the one that's emitted when the atom drops down in one stage. The energy that's going to be emitted as the atom drops from level 2 down to the ground state, well, that must actually be the same as the energy that went in when it went from the ground state up to level 2. So we don't need to do any extra working out, we can just put the same answer in. 1.94 times 10 to the minus 18 joules. How do we find the wavelength of the photon? Well, if we use E equals HF, then that means we can find the frequency. E divided by H, which is 1.94 times 10 to the minus 18 divided by 6.63 times 10 to the minus 34, 2.93 times 10 to the 15, that's frequency, so it's hertz. And then to find the wavelength, we know that for a wave, speed equals frequency times wavelength, so wavelength equals speed divided by frequency, and we know we're dealing with radiation, so we know what the speed is. It's the speed of light, speed of electromagnetic radiation, 3.0 times 10 to the 8 divided by 2.93 times 10 to the 15, 1.02 times 10 to the minus 7 metres. Now we could have done this in fewer steps if we'd used the equation E equals hc over lambda. I just preferred to find the frequency because I'm so familiar with the equation in that form, that's the form I like to keep it in. But there's absolutely nothing wrong with using that formula.